Hello guys, welcome back to our discussions on the bending of prismatic beams. So in this topic we are going to look at a new subtopic here, which is on the plane frame structures. So as we can see in these figures, a frame structure is actually can be made up of rigidly connected members, where each member here can be treated as a beam. So as we look at this figure here, so we have one frame structure which is consists of three beams element, which is arranged to look something like this. So in plane frame structures, the axial lobes exist, thus the axial deformations occurs and must be considered. Element of frame structure can be in different orientations, whether we have this a cool pose like structures, or we can have a structure that is maybe where each member may be inclined to certain angles from the horizontal axis. If we can recall back when we discussed about the beam structures, where at each one nodal point we have 2 degrees of freedom, which is I draw this in the positive directions of the translations and also the rotation. This is for the beam. But for a single frame elements, so as shown in this figure, we have a single frame elements, where at one nodal point, instead of having 2 degrees of freedom, at one node or nodal point for a beam for a single frame element, we have to include the axial translations here or deformations, and to include the vertical and also the rotations. So that's mean here for the frame, for at one nodal point we have 3 degrees of freedoms. So in global coordinate system, as we can see here, we have the vertical, the horizontal translation, and also the rotations at nodes number 1, and we have the horizontal, vertical translations, and also the rotation at nodes number 2. So that's mean here for a single frame element we have 6 degrees of freedom. So since a frame can be organized in any orientations, so it is very important to look at or to analyze one or a single beam element as shown in the figure, and we view this in the global coordinate system and also in the local coordinate system here. So first we look at this the local coordinate system, where in local coordinate system the x-axis usually is arranged and spanning along the elements, and the y-axis is tangential to the element, and we label this with x prime and y prime. This is actually to shows the local coordinate system. While for the global coordinate system, the Cartesian x and y, which is as given here. So this is the standard XY coordinate system for the Cartesian coordinate systems. So in terms of the deformation, if we first view the deformations that is acting on the local coordinate system, then at nodes number 1, for example, here we have Q1, we have Q2, which is referred to the translations along the x-axis and y-axis. Then we have the rotation applied at nodes number 1, but in local it is viewed as Q3 primes. At nodes number 2, then we can draw this the deformations in x and y direction, which is here we have translations Q4 prime, Q5 prime, and also the rotations at nodes number 2, which is given by Q8, Q6 prime, Q6 prime. So this is if we view all these deformations in local coordinate systems. But if we are working with the whole frame, or for the whole systems, or for the whole structure that we are going to solve, then it is very important to view or to translate all the deformations in local coordinate systems into the global coordinate system. The nodal displacement vector in global coordinate system is given by Q, where Q1 and Q2, Q4 and Q5 are actually representing the translations both in x and y prime in x and y directions, while Q6, 3 and Q6 representing the rotation at each nodes. And the nodal displacement vector in local coordinate system is given by Q prime, which is Q1 and Q2 prime, Q4 and Q5 prime, representing the translation both in x and x prime and y prime in local coordinate systems, Q3 and Q6, which is refers to the rotation at both nodal points. So it is very important here to understand that the rotation is actually similar whether we view this in the local or global coordinate system, so it is not affected. So note that the rotation component Qt prime and Q3 equal to Q3 and Q6 prime equal to Q6, which is there is no difference in terms of rotations. However, as I mentioned just now, since we are first working in the local coordinate system, so later we have to transform all the displacement and rotations or the deformation which is we derive or work in the local coordinate system and transfer it into the global coordinate system by applying these transformations matrix. So if we still can remember the L here, which is just the term that contain the cos theta, and M here, which is the term that consists of sine theta. So this transformation matrix is just actually the matrix that we use to do the transformation from the local coordinate system into the global coordinate system, or on the other way around as well. So Q2 prime, Q3 prime, Q5 prime, and Q6 prime are the beam's degree of freedoms, while Q1 prime and Q4 prime are similar to the displacement of 1D elements. So combining this stiffness metric for a beam and 1D elements give stiffness metric for frames elements written in local coordinate system as shown here. So as we can see here, for one beam structure we have 3 degrees of freedoms at one nodal point. So for one beam's elements we have 6 degrees of freedom. So we can expect here that our element stiffness metric will have 6 by 6 in terms of its size. Since the element stiffness metric that shown just now is written in the local coordinate system, so it is very important to transform it into the global coordinate system by using this approach. So starting from the internal strain energy, which is obtained from the potential energy equations, so we apply the transformations to our element stiffness matrix, which we multiply by the transformations matrix here, which is give the expression for our element stiffness metric in global coordinate system by these expressions. So this element stiffness metric must be applied to each single frame elements considered in our problem. So let's say we have 3 elements which are organized to have something like this. So we will have K1, K2 and K3, which is to obtain the global element stiffness metric, then we have to add all of these K from each element. And of course, to add all of these element stiffness metric, so we have to add it according to its matrix addresses. So at this stage, actually, we should be able to prepare the K metric in our system of linear equations, which is can be written in the form of KQ equal to F. So this is actually, I put it G here to refer it to the global or to the whole complete system of our structures. So now we're done with K. So let's look what will happen to the F. So let's look at the element that is subjected to a uniform distributed load as shown in these figures. So as we can see here, this distributed load is actually acting on an element that is inclined to a certain angle theta, and it's spanning on the whole element from nodes 1 until nodes 2. So applying the similar approach that we did on the beam elements, so this uniform distributed load must be first transferred into the its equivalence nodal force and moments as shown here. So these negative signs to the rotation is actually to comply with the positive sign conventions as we discussed before. So again here, as we can see, our global coordinate system is actually spanning in these two directions, x and y. So everything that is initially located or analyzed in the local coordinate system somehow must be transferred into the global coordinate system by multiplying it by its transformations matrix. So let me first look at is our first example, where we have a portal frame structure as shown here, and the question here asking us to determine the displacement and rotation at joint 1 and 2, which is somewhere there, which is exactly at this point. So as you can see here, this portal frame is subjected to uniform distributed load with this amount, and we have also the axial load, which is 3,000 pounds, which is acting at node number 1. The frame has three elements. Element number 1, which is spanning from nodes 1 to 2, element number 2 spanning from 1 to 3, and element number 3 spanning from 2 to 4. The size or geometry of the structure is given as 12 feet length and 8 feet high. The material properties is provided here as well, which is the modulus of elasticity, its second moment of inertia, and the cross-sectional area, which is given as 6.8 inch square. So as usual, before we start solving finite elements to our structure, then it is very important to establish the its element connectivity. So in this case, we provide the element connectivity, or we suggest this element connectivity, which is for element number 1 is connected from 1 to 2, element number 2 from 3 to 1, and element number 4 from 4 to 2. And this element connectivity is actually very important to establish how one element is connected between each other. Not only that, it is also important in setting up our system of linear equation, especially in setting up its local element stiffness matrix. So in my case, I like to draw the directions how one element is connected. For example, element number 1 is connected from 1 to 2, then I will draw the directions of its connectivity. For element number 2 is connected from 3 to 1, so I will draw the element connectivity. Then similarly for the element number 3 is connected from 4 to 2, then I will draw. This is the directions of how each element is connected between each nodal points. And this is the first stage that I will do when I solving the portal frame structure using finite elements methods. So at this stage, it is very important as well to look at the boundary conditions. But before that, it is convenient to level or to draw all the degrees of freedom that we have at each nodal point. So we have Q1, Q2, 3, 4, 5, 6. Here will be 7, 8, 9, 10, 11, and 12. So if we look at these boundary conditions, where at nodes number 3 here, where this part of our proton frame is having fixed boundary conditions, so that means there will be no possible translations in all directions at this particular cross-sectional area at nodes number 3. So in this case, I can say that there will be no displacement. Q7 will be equal to 0, Q8 will be equal to 0, and since it's also fixed, there will be no translation as well. So similarly at nodes number 4 here, where the displacement in all directions and also the rotation will be equal to 0. At node number 1 and node number 2, these two joint is we leave is as a free joint here, so there will be a possible translations or deformations in all directions at these two points. So in this case, by looking at its boundary conditions, so from there we can expect we will have to develop 6 equations for our system of linear equations. And furthermore, since our frame structure consists of 3 elements, so we can expect that we will have 3 element stiffness matrix K1, K2, and also K3. So dealing with the loading, we have 2 types of forces applied here, which is in the form of uniform distributed load and also the point load. So for the uniform distributed load, we have to transform it into the equivalence nodal force and moments as we did in the beam elements in the previous lectures. Since we have this uniform distributed load that is pointing downward, so we will expect that the beam here will bending this direction. So to make this direction consistent with the positive convention, so we will have negative value there, and there. So we will have something which is like this. And first, let's we look at the how we can identify the angle theta of our frame elements. So angle theta is always measured from the horizontal axis. This I take it horizontal axis for each element, which is will look something like that. So then we know that element number 1 is connected from 1 to 2, so we can expect that the theta for element number 1, which is equal to 0 degrees. For the element number 2, it is connected from 3 to 1, so we are from here to there. Then the element number 2 here will have the angle which is equal to 90 degrees. And similar to this one as well, the angle, which is the angle theta, which is equal to 90 degrees. But what will happen if, for example, the connections for element number 2, for example here, instead it is connected from 3 to 1, but let's say we say this element now is connected from 1 to 2. So in this case, if our starting point here, where the element number 2 is connected from 1 to nodes 3, so we start here. So I will draw a line, horizontal line at nodes number 1 and start measuring the angle. So in this case, for element number 2, if for example in terms of its element connectivity, it is connected from 1 to 3, then the angle theta here will be 270 degrees, or this is also equivalent to negative 90 degree if we measure it from here to this direction. But in my case, I always like to make my calculations consistent, following only anti-clockwise direction. So I will draw the line from where the connections is starts. Then I start to looping the angle until it reach or it found the element. So in this case, we have theta equal to 270 degrees for element number 2. So this element connectivity is very important in setting up our element stiffness matrix. So for element number 1, this element is connected from 1 to nodes number 2, where at nodes number 1 we have the degrees of freedom, which is starting from 1, 2, 3, 4, 5 and 6. So when we write our element stiffness matrix for element number 1, then it is I think very important to write this index on the top and on the side of our element stiffness matrix as shown here. So this is for element number 1, where angle theta equal to 0 degrees. So on the top of my element stiffness matrix of element number 1, I will put the index numbering starting from nodes number 1, which is start from 1, 2, 3, and for the nodes number 2 I have index 4, 5 and 6, so I will put here as well. So this is my element stiffness matrix for element number 1. So it should be noted as well, since the angles of my element is 0 degree, so the element stiffness matrix in local coordinate system is similar to the one in global coordinate system. For element number 2, on the other hand, as we look at its connectivity, so it's start from nodes number 3 to nodes number 1. So in terms of our element stiffness matrix, so we have to set up our element stiffness matrix to follow the index, which is starting from Q7, 8, 9, which is where it starts, and followed by Q1, Q2, Q3, where this element ends here. So this is the example of local element stiffness matrix for element number 2, which is I have all the coefficients set up, but in terms of its address here, I have I will write from the starting nodes here, where I have Q7, Q8, Q9, and the index where the element n, which is followed by q1, q2 and q3. So at the side here, I will write the same as well. The index to my elements of stiffness matrix. The last element that we have here, which is element number 3, and again here element number 3 is connected from nodes number 4 to nodes number 2. So in terms of the index for my element stiffness matrix for element number 3, I will have the index which is starting from Q10, 11, 12, and then followed by 4, 5, and 6. So since the element number 3 having the angles 90 degree, which is equal to element number 2, so the value for the coefficient inside the matrix will be the same. It's just the matter of the index will be different. So for the element number 3, so instead of having 7, 8, 9, 1, 2, 3, so the index on the top here will be replaced by the one that we have here, 10, 11, 12, 4, 5, 6. So here I will put 10, 11, 12, 4, 5, and 6. So this is the matrix element stiffness matrix for element number 3. So coming back to these boundary conditions, which is we have identified which component will active and which component which is inactive based on the boundary conditions applied to our systems. So for example, for element number 1 here, where all components here are active, so our K matrix will be all active. So our K matrix will be all active. So we have 6 by 6 full matrix here. For element number 2, however, we knows that Q7, Q8 and Q9, and due to this boundary condition there will be no translations and rotations exist at nodes number 3. So we can apply this to our element stiffness matrix for element number 2 by eliminating their respective rows and column. So if I am working on my element number 2, so we know that Q7, Q8 and Q9, which is under fixed boundary conditions, so there will be no displacement, so I can eliminate this row and column number 7, 8 and 9. So this is the only metric that active for my element number 2. But again, this metric is still written in the local coordinate system, which is later we have to convert it into the global coordinate system by multiplying by the Kerr's transformation matrix. For the element number 3, however, we have the same situation as the element number 2, where at nodes number 4 we have Q10, 11 and 12, which is equal to 0, which we have inactive deformation there. So coming back to the element stiffness metric for element number 3, so from there we can eliminate these respective index or address which have 0 deformation, which is in this case we have 10, 11, 12, and we eliminate these row 10, 11 and 12 as well. So as we can see here, this is again the metric that having active with active index Q4, 5 and 6. Even though as we look or we compare between K2 and K3, we have the same values of coefficients in the in our matrix, but their index are not the same. So this is where the elements connectivities plays its important role here. So when we have set up our element stiffness matrix, which is at this stage we are still working in the local coordinate system, then applying this transformation matrix, so we actually able to transform our element stiffness metric in local coordinate system into the one that is written in the global coordinate system. And we have to do this to all our element stiffness metrics for each element. And this is the element stiffness metric written in global coordinate system for the element number 2 and element number 3, which is, as we mentioned just now, the first 3 rows and columns, which is where we have the fixed boundary conditions, so we can eliminate it. So only our active elements, which is this 3 by 3 matrix. So for the element number 2, so I have element 1, 2, 3. So for this element number 3, I have index 4, 5 and 6, which is having active elements. So when we have this done, we have applied the boundary conditions. We eliminate the element rows and column which is not important in our calculation. Then we assemble all of this. So we add K1, we add it with K2 and K3 according to its index numbering, or you can call it as address as well. So you can develop instead of having, supposed to be we have 12 by 12 big matrix, but after we apply the boundary conditions, we eliminate the unnecessary elements or index that are inactive. So let us to only a 6 by 6 matrix that representing the whole systems or the whole frame structure that we are going to analyze. So again, we can label here. So this is the active index that we are going to solve in our analysis later, which is spanning from 1, 2, 3, 4 and 5 until 6. So this is our global stiffness metric of the whole structure that we are going to solve after we consider its boundary conditions. And we have discussed a bit on the how we can transform these uniform distributed load into the its equivalence nodal force and moment, which is very similar to the one that we applied to the beam problems. So if you look at this structures or elements here, we have P1, P2, P3, P4, P5 and P6. So which is at note number 1 here, where our P1 which is equal to 0. Why? Because the way we transform this uniform distributed load, which is we apply similar to the beam problem, where P the loads, there is no load in the axial directions. So initially the value here, which is actually 0, we have this value P2, P3, P4 also equal to 0, P5, and we have P6. But at node number 1 we have additional load applied in the axial direction as well. So we have actually 0 plus 3000. So that's why we have this number here. So P4, there is no force applied in this direction contributed from uniform distributed load, so it will maintain equal to 0 there. So the rest is as usual, where negative 3000 here is actually contributed from PL over 2, and negative 72,000 here, which is actually contributed from PL square over 12. So once we have this done, we can set up our system of linear equation in the form of KQ equal to F. So this is our K matrix. So this is our column vector of forces, and this is the unknowns parameter that we are going to solve by solving the system of linear equations, whether using any SLE solver. Then actually we can obtain the final solution for the all value of Q's, which is given by these numbers here. Alright, I think that's all for this session. If you have any problem, then we can communicate through the UTM e-learning system. Thank you very much.